And this is it, the final Level 3 Cambridge Technical and Engineering revision session, Unit 3, Principles of Mechanical Engineering, Question 6, Part B, Parts 1 and 2, the final part of the exam. So we've had a skier, he's gone off the jump, and now the skier is using the chairlift to ascend to the top of the slope. The chair has a mass of 300 kilograms and is travelling at 0.8 meters per second. Before the skier sits down, the skier is stationary, so he's going to be 0 meters per second. Assuming conservation of momentum, determine conservation of momentum. Determine the combined velocity of the skier and the chair immediately after the skier sits down. Well, I know that the skier weighs 80 kilograms. We know that from the previous question. So we've effectively got a chairlift of some description that's moving in that direction, 0.8 meters per second, 300 kilograms. Okay, so remember we're talking about dynamics, so the conservation of momentum, well there's momentum, is the mass times velocity. Okay, so the momentum here at this side is going to be 300 times 0.8. So we've got a value of 240 kilogram per meters. There we go. And that is going to bump into our skier. Who at the moment has no momentum, 80 times 0. But when that and that come together, we're going to end up with a system that it's gone from 300 kilograms to 380 kilograms. Okay, so what will be the new velocity? So we've got mass times velocity on this side is equal to mass times the velocity on this side. Right. So if we rearrange for velocity, multiplication, so we'll end up with 240 divided by 380 going to be equal to 240 divided by 380, 0.63 meters per second. Just check that. If we take that and multiply it by 380, it should give us 240. There we go. So the momentum is the mass times the acceleration on this side, or mass times velocity on this side, has to be equal to conserve the momentum, that the increased mass on this side, obviously a reduced velocity, so that the two sides match. Right, so part 2, the chair has been modelled as a beam with a worst case loading scenario as shown in figure 13. So we have 1.8 meters, we have the weight of the beam, which is UDL, uniformly distributed load. So we've got 2,100 newtons per meter, but we've got 1.8 meters. That's going to be key. And we've got a point load of 2,000 newtons. That's a couple of hundred kilograms. So it's probably 2 skiers. Calculate the tension in each of the supporting cables under this loading. So we've got one cable on either side that's going to share this total load. So let's calculate the total load first. We've got 21 newtons per meter we've got 1.8 metres there, so the total load of that part of the lift itself is going to be 3780, and we've got a point load, an additional 2000 newtons. There's our two skiers, so plus 2000 gives us 5780. I just realised what I've done there. I haven't moved it up so you can see what I'm doing, so we'll just go through that very quickly again. So here's our lift. We've got 1.8 metres here. We've got a uniformly distributed load, hence the little, that's what these little symbols mean. 2,100 newtons per metre. We've got 1.8 metres. So to calculate the total load, we've got an additional point load of 2,000 newtons. So 2,100 times 1.8 is 3780, plus the point load of 2,000 newtons gives us a total of 5,780 newtons, but it's shared across these two beams. So 5780 divided by 2 means that we'll get in each, calculate tension in each, so the tension in each one would be 2,890 newtons. I hope you found the videos useful, and I hope you do really well in the exam.